Hello viewers, welcome to our lesson on combinations, part of the chapter Permutations and Combinations. Now, the word combinations is in general known to you. What kind of a combination am I going to wear today? Is it red and white or white and black? But is red and white same or different from white and red? No. In language of combinations, there is no difference in the way I read out the combination, and that is what we are going to learn in a more mathematical form today. Starting with a simple example. Suppose I have 4 people available, out of which 3 have to be selected for a certain committee. Now, in how many ways can I make such selection? Think about it. I have 4 persons and I want to select 3. So, I have a person A, B, C and D. I may select A, B and C or A, B and D or A, C and D or B, C and D. Can I do it in any other different way? How about if I say I select C, A and B for that committee? Is it any different from a committee which comprises of A, B and C? No. And that is the word combination means, and that is what we are going to learn today. The position, the order is not important. Who I have selected is of importance. And so, we define the word combinations as number of different selections that can be made by taking some or all of a number of objects irrespective of their arrangements. And what we are interested in is finding how many such combinations can be made. That is, the number of combinations is what interests us. There is a simple result which says that the number of all combinations of n distinct objects taking r at a time is given by and denoted by NCR, written in the form as you see here, with the value n factorial by n minus r factorial into r factorial. Now, where is this result coming from? Let us take a look at a simple explanation for this. Suppose I assume that the number of combinations of n distinct objects taken r at a time to be x. Now, in one of these x ways, I am looking at r objects. So, as in our previous example, one of the selection of 3 out of 4 could have been A, B and C. In this selection, one of these x ways, there could be r objects which can be permutated in r factorial ways. So, that is with your A, B and C, as in our previous example, there could have been 3 factorial permutations. Therefore, x times r factorial should give rise to the total number of permutations of n objects taken r at a time, and therefore, x must be equal to npr upon r factorial. But npr was nothing but n factorial by n minus r factorial, and therefore, I get the result which says that the number of combinations of n distinct objects taken r at a time to be same as n factorial by n minus r factorial into r factorial. And with this formula ready, we are now ready to deal with problems where the conditions are stated in words and you have to now translate them and use this result to figure out the total number of combinations possible within the given condition. Our first problem says a committee of 12 is to be formed from 8 women and 7 men. In how many ways can this be done if at least 5 women have to be included in the committee? And in how many of these committees the women are in majority? So, we are looking at out of the 12, there has to be at least 5 women in our first part. So, when we say at least 5, you may have more than 5. So, how many such possibilities are there? I may have a committee which comprises of 5 women and 7 men, 6 women and 6 men, 7 women and 5 men, or 8 women and 4 men. So, we are looking at number of ways I can select 5 women out of 8 available and 7 men out of the 7 men available. Therefore, the total number of ways in which the first case can be done will become 8C5, selecting 5 out of 8 into 7C7. 7 men out of 7 can be selected in 7C7. And why do I have a product there? Because of fundamental principle of counting, which says that the number of ways in which the women can be selected and the number of ways in which men can be selected will be the product of the number of ways in which both can be done. Similarly, the second case can be done in 866 into 7C6 ways plus 8C7 into 7C5 plus 8C8 into 7C4. This leads to a calculation which is much more simplified now, because we are dividing by n minus r factorial into r factorial, and that turns out to be same as 407 when added up. So, you are looking at 407 ways in which this can be done. In the second part of the problem, the women have to stay in majority. Now, when you are looking at women in majority, what are the cases possible? Out of these, we are looking at the third and the fourth case, that is, there should be 7 women and 5 men or 8 women and 4 men, and therefore, the total number of ways in which such a committee can be formed will be 8C7 into 7C5 plus, because we are translating or into an addition, plus 8C8 into 7C4, giving rise to a number as 203. Our next question is also on combinations, but it talks about something different, not committees, not teams, but points given and lines to be constructed. The question says there are 10 points in a plane, of which 4 are collinear. How many different straight lines can be drawn by joining these points? Now, what we are looking at is an understanding that lines are constructed by taking 2 points at a time. Given 10 points, the number of straight lines that can be defined will be 10C2. What about these 4 points which are collinear? If I take out of these 4 points 2 at a time, the number of lines that I can talk about is 4C2, but then these are all on the same line. So, this is an extra number that I am getting. At the same time, all of these do make one line at least. So, what will be our total counting? The total number of straight lines that can be formed will be nothing but 10C2 minus 4C2, because they were all of the same kind and that was not giving rise to any unique line. But then when I subtract this 4C2, I am also removing the number of lines that were coming across from that number 4C2, giving rise to one line on which all those 4 points lie. So, I have to add back that 1, and therefore, the total number of lines that I get on calculation turns out to be same as 40. Now, the same understanding can be used for a problem like this, where it says how many diagonals are there in a polygon with n sides. That is interesting. Diagonals are again nothing but segments that can be drawn by joining the 2 vertices of the polygon. That means, if I take all the lines that can be formed by taking the n points 2 at a time, which is NC2, does that become the number of diagonals? No, because out of these there will also be n sides which are forming line segments in this counting, but they are not the diagonals. So, the number of diagonals will be NC2 minus n. So, if you simplify this, it gives rise to a nice little result n times of n minus 3 by 2, which you may use anywhere else as well to figure out how many diagonals a polygon with n sides will have. Here is another problem. How many 5-letter words containing 3 vowels and 2 consonants can be formed using the letters of the word equation? In how many of these words do the 2 consonants occur together? Now, the word equation is an interesting word. Interesting because you find all 5 vowels coming in this word. So, I have 5 vowels E, U, A, I, O all appearing here, and I have 3 consonants Q, T and N. Now, the question asks us to form 5-letter words which has 3 vowels and 2 consonants. That means, I have to select 3 vowels out of the 5 and 2 consonants out of the 3 given consonants. That can be done in how many ways? Out of 5, I can select 3 in 5C3 ways. Out of 3 consonants, I can select 2 in 3C2. So, the total number of ways such selection can be done will be 5C3 into 3C2. So, is that the number of ways the words are going to be formed? Well, no. You may be able to permutate those 5 letters to form words. So, I have now 5 letters and they can be permutated in 5 factorial ways. And therefore, again my fundamental principle of counting, the total number of words that can be formed will be 5C3 into 3C2, that is the number of selections, into the number of arrangements, which is 5 factorial. It comes out to be same as 3600. Now, the second part says, in how many of these words do the consonants occur together? So, we want the consonants to stay together. So, what would one do now again? We are looking at 5 vowels, 3 consonants and 3 vowels to be selected out of 5, that can be done in 5C3. 2 consonants can be selected out of 3 in 3C2. So, the product gives us the number of ways the selection can be done. How about arrangement when the 2 consonants occur together? For the 2 consonants to occur together, I have to make a bundle of them, and within the bundle I can arrange them in 2 factorial ways, but that bundle and the other 3 vowels make 4 objects which can be arranged in 4 factorial ways. So, we are looking at 4 factorial into 2 factorial to be the number of ways in which the consonants stay together, but the arrangements can be done. Considering this calculation and the calculation of the number of ways the selection can be done, the total words that can be formed will be 5C3 into 3C2 into 4 factorial into 2 factorial. So, again the fundamental principle of counting comes in use to find this product, which is product of selections and arrangements, and gives rise to 1440 such words that can be formed with this condition known to us. In the last question, we have used 3 important things: permutations, combinations and the fundamental principle of counting. Selection word is associated with combinations, arrangement with permutations, and when you do selection and permutations together, we are also making use of the fundamental principle of counting to find the number of ways in which selection and then the arrangement can be done. The last 4 lessons that we have done in this series have covered possibly all aspects of the chapter Permutations and Combinations of your NCERT book. I hope you have stayed with us and you have done the required practice to master this concept. I hope you are going to now go and try some more. All the best to all of you.